They're observations made with reference frame to one another. Okay, so objects now take on kind of a new frame of reference. It might not be that I'm looking at an object from where I'm sitting. It might be that I'm looking at it at a different view. Okay, maybe I'm moving with the object. Maybe I'm moving against the object. But what we're looking at is what's going to be an object's velocity relative to something else, rather than relative to the ground or relative to my position or something like that. Okay. I'm going to just kind of talk through this, so you don't have to necessarily have this part down in your notes. But if I have two trains that are traveling 80 kilometers per hour, so same velocity, and they're traveling toward each other. Okay, so let's just visualize what's happening here. You're standing on the side watching these two trains travel toward each other. Okay, so if I'm standing on or beside those train tracks watching these trains come toward each other, I would be able to see that each of these looks to be traveling the same speed, but in opposite directions. Okay, I should be able to see that. Not necessarily that I would be able to tell it's 80 kilometers per hour, but I should be able to tell that these two objects are traveling at essentially the same speed. Okay, do we all agree at that point? We're standing still. Nothing's changing our frame of reference at all. We're being able to see both of those trains come at each other. If I was going to stand on now one of the trains, and I'm traveling 80 kilometers per hour, and another train is traveling at me 80 kilometers per hour, it would seem like I'm traveling twice as fast. Okay, because I'm moving in one direction and something is coming at me with equal speed from another direction, right? We're closing in that distance in twice the time. Okay, so let's say that there's 100 meters between us. We're each going to cover a meter every second, or a meter every same time interval, which means we're closing that gap in twice the time. So it seems, in half the time. So it seems like we're traveling 2 times as fast. Does that make sense? Okay. So if I am driving down the highway and I'm going 70 and I come up on a car that's going only 55, how fast does it feel like that car in front of me is going? Really slow or really fast? Really slow. It feels like they're going really slow. It would theoretically, to me, feel like they're going only 15 miles an hour, right? Because originally I was traveling 70. They're only going 55. To me, it seems like they're only traveling 15 miles an hour, okay? Because we're traveling at such a rate, we come up on something that's slower, and it feels to us like we're slowing way down, even though we're still going 55 miles an hour, okay? So do we understand kind of the frame of reference that we're talking about here? Okay. So questions so far about this. This is what we call straight line relative velocity, okay, or same line velocity. Those two examples that we talked about are called same line velocity. And that's when we use just simple addition or subtraction to solve for that resultant vector, okay, or that missing vector. So for these relative velocity problems, you can't get too caught up in really little specific details. You've got to take a step back and look at the bigger picture. Okay? Visualize yourself in that situation so that you can look at the big picture here. Okay? So let's look at an example for same line velocity. Okay, Sam is skating 3 meters per second west. If I push him so that he ends up traveling 5.3 meters per second west, what was the speed of my push? Okay, so let's think about this. I want you to start kind of working through it, see how you would go about solving this, and then I'll kind of show you what I'm talking about here with our vector addition. So I want you to think about how you would solve it first, and then I'm going to try and attempt to show you how to do the vector addition part. All right, it tells us that Sam is going 3 meters per second west. Okay, and then it says I end up pushing him. Okay, but my resultant, I know, I'm going to put the resultant right below it, makes him go 5.3 meters per second west. Okay, so was my push in the west direction, or was it against Sam? Was it with him or was it against him? It was with him. So when I add these vectors tail to tip, I need to add my push, right? That's the velocity of the push, adding on to that. Yeah, so I'm going to subtract. I'm going to take 5.3, which is my resultant, minus 3.0. And that means I pushed him with a velocity of 2.3 meters per second. Okay? If Sam had went with 3 meters per second, and if after I pushed him he ended up traveling 1 meter per second west, where would that mean my push would have had to go in what direction? It would have had to go east. So that means when I add my push tail to tip, it ends up looking something like that. I pushed him 2 meters per second east. Okay, so do we see the difference there with our resultant? We have to understand which vectors are resultant in this case. Okay, and all of these relative velocities, finding that resultant vector is really, really, really important. Okay, so this is same line velocity. This is pretty simple. Now we're going to move on to two-dimensional, so things that move horizontally and vertically. Okay. If we're not in the same line, we're going to use vector addition to find velocity of one object with relation to the other. Vector addition, again, is tail to tip. You solve your hypotenuse. You use second tangent to find your angle. You guys know how to do all of that. Okay? Now we're just taking on a little bit different overall goal. With these relative velocity problems, it's very, very, very important that you draw the diagram. Okay, you draw out what vectors are being represented and you identify your resultant. Okay, whenever we're trying to determine which one our resultant is, it's going to be the overall goal of our process. Okay, and we do a lot of examples in relative velocities about using river currents, using air currents that push us one way or another. Okay, those are the kind of problems that we work with relative velocity. So if I'm swimming across the river and the current's pushing me downstream, what's going to be my overall velocity, right? That's going to be the kind of problems that we deal with. So when we're trying to identify our diagram and find our resultant vector, we have to understand that your resultant vector should be the overall final velocity. The overall goal of our person has to be our resultant vector. Okay, so if we get a problem that tells us this person is really trying to end up straight across the river from where he started, that means that needs to be our resultant vector, and we're going to add our vectors tail to tip to get to that point. Okay, so identifying the resultant in these problems is kind of the trickiest part, but if you can get your diagram drawn correctly, the math that goes into it is very simple. Right? Just Pythagorean theorem type stuff. Okay? But drawing that diagram and finding that resultant is extremely important. Okay? So once we've identified which should be our resultant, we have to add our other vectors tail to tip to get to that point. Okay? Okay, a lot of these relative velocity problems have to do with driving across a river or a stream or flying in the air, something that's going to be able to, where you're influenced by an outside force like wind or a current or something like that. Okay? So here's our example here. A boat is attempting to drive straight across the river to get to the other side. Okay? Its goal is to end up straight across from where it started. So here's our origin, right? Here's our starting point. And our resultant is our black vector here, right? Our resultant goes from our origin to the tip of our last vector. So that's going to be our resultant. Our goal is to end up exactly across from where we started. Okay, so that should be the first vector that we draw. And when we talk about river currents, this is kind of usually the diagram I use, like straight across is usually just to the north. Things like that. You could draw your diagrams differently, but I just try to keep it consistent and use the easiest coordinates that we have. Okay. So our goal is to end up straight across from where we started. That's the first vector that you've drawn. The other vectors we haven't talked about yet, so you don't have to draw those in yet. You can if you want, but we're going to talk about each of them individually, so we'll put them on our diagram one at a time. Okay. The river is flowing at a rate of 1.2 meters per second west. So which of these vectors, the yellow or the green, is our river current? Yellow or green? Green. Green is our river current because it's going straight west. Okay, straight west. So now I want you to kind of put yourself on that shore. Okay, put yourself at the starting point at the origin right here and think, okay, if the river's going to push me west or to the left, and my goal is to end up straight across from where I start, which way do I need to leave the riverbank? Do I need to leave it to my right or to my left? I need to leave it to my right. I need to leave somewhere out this way so that the current pushes me back to where I start. Does that make sense? That's what these relative velocity problems are about, is getting you to picture what's happening in this problem. Okay, so that means if the boat needs to be traveling at 1.8 meters per second on its path straight across the river, what speed and at what angle must they leave the shore? Okay, so we were told that our river current is 1.2 meters per second. Where does our 1.8 meters per second need to go? On our resultant or on our... What do we think? The yellow? Okay, it tells us the boat needs to be traveling 1.8 meters per second on its path straight across the river. So that means that's its overall goal. Where does that need to go then? With the resultant, so with our black vector. Because it asks us what speed and at what angle must they leave the shore. So that means we're finding out what our hypotenuse is. We have to find out what speed do we need to leave and at what angle do we have to leave at to get to our final destination at the right speed. Okay? Are we on the same page so far? All right. So now I need to find my hypotenuse and I need to find this angle right here. All right, and I'm going to go about solving for my hypotenuse using Pythagorean theorem. Good, so I'm going to take 1.85 squared plus 1.20 squared, and I'll take the square root of that whole term. Okay, and I got about 2.21 meters per second. Yeah? 2.205 or 2.21. And then how do I go about solving for my angle here? Second tangent. Okay, so second tangent of what over what? 1.2 over 1.85. I would usually always go with the numbers we were given, right? I want to use second tangent. I don't want to use second sine or second cosine, because what if I solved this portion of it incorrectly? Okay, then I'm off both places. So use the numbers you were given. So we'll take second tangent of 1.2 over 1.85. Make sure that your calculator's in degrees, which gives me about 33 degrees. Okay, so my final answer means I need to leave the shore at 2.21 meters per second at 33 degrees, blank of blank. What do we see this angle is? East of north. Good, very good. East of north. It's touching the north axis, and then we decide, is it east of north or west of north? And we see that it opens east of north. Very good. Okay. All right, now it says the same boat leaves the shore driving straight across the river with a speed of 1.9. If the current's pushing him west at 1.45, what's his actual velocity? Okay, so this time he leaves just going straight across, and the river's going to push him. Okay, so is he going to end up to the west or to the east of where he started? west, right? So picture what's happening here. You're on your boat, you're trying to drive straight across the river, but my current is pushing me to the west. So I'm going to end up to the left or west of where I started. So which of these vectors is going to be my resultant? The black vector is my resultant because I'm leaving here. The river's pushing me that way, which means my resultant, I'm going to end up moving at this velocity at a certain angle from my starting point. Okay? So I know drawing this diagram is the most important part here. Sorry, I'll give you a little bit to finish getting it written down and we'll work through it. So if I'm going to label this side of this vector of my diagram, what's it going to be labeled as? 1.45, because that's my current, right? It's moving west. I'm leaving straight across at 1.9, and I want to solve for my hypotenuse. Okay, so I'll take second square root of 1.45 squared plus 1.9 squared. Do we agree with those numbers or not quite? Close enough? Okay, so I found my 2.4 by taking Pythagorean theorem of both my sides, solving that hypotenuse. I took second tangent of 1.45, which is my opposite side, over 1.9, which is my adjacent side. And I got 37.4 degrees. What's my angle going to be here? What will my angle be? What of what? West of north. Okay, because here's my coordinates. It's touching my north axis. I decide it goes west of north. Okay. I want you to go ahead and try this one on your own. Okay, try this one on your own. They're riding on a ferry that's traveling east. She rolls the marble with a velocity of 0.75 meters per second north, which happens to be straight across the deck. What's the velocity of the marble? Okay, so if the boat is traveling 4 meters per second east, that means that all of these people have to be traveling 4 meters per second east. So that's one of our velocity vectors. Okay, that means the marble has to be initially traveling 4.0 meters per second east, and then we're going to roll it. Okay, so I want you to try this one on your own. So go ahead and get it written down, and then we'll start working through our diagram and our overall process here. Problem here, do we have to convert kilometers per hour to meters per second? No, we don't have to because both of our velocities are already in kilometers per hour. We can leave that. That's fine. Okay, that means our other answer, our wind current answer, should be also in kilometers per hour. Okay, so let's go ahead and take a look here at our vectors. Okay, we've got a plane that's flying 200 kilometers north. Okay, and it tells us the plane's actual velocity is 18 degrees east of north at 243. Have we identified which of these should be our resultant vector? Yeah, the last one I just talked about, that 243.2. So I'm going to draw a resultant here. 243.2. I drew it in the northeast direction, but which side does my angle need to go on? Top or the bottom? It needs to go right here, right? It needs to connect my two vectors, first of all. So this is 18 degrees, which means my current needs to be going, or my wind needs to be pushing me which direction? To the east or to the west? My current's going to go from... Yeah, it needs to connect my vector to my resultant. My resultant always goes from the origin to the tip of my last vector. That means the current has to be pushing me east, or the wind has to be pushing me east. Okay? Has to connect those two vectors. So here's our vectors added tail to tip to get to our resultant. You did a good job identifying this as our resultant vector, but then we have to understand that the other two have to be added tail to tip to get there. Okay? So how do I go about solving for this side? Yeah, you could use Pythagorean theorem, you could use your trig functions, you can do it a couple different ways. Okay, if I'm going to use Pythagorean theorem, I'm going to take 243.2 squared equals 200 squared plus b squared. And what do we get for the velocity of our wind? About 138.4. Okay, couldn't we also solve using our 18-degree angle? Okay, which could I use? I could use any of my really trig functions here. Okay, if I use 18 and my hypotenuse and my opposite side, what trig function might I use? So if I take sine of 18 degrees equals opposite over 243.2. I'm getting a little different answer.